In this episode, we're going to take the idea of access control and make it precise, because security becomes far more reliable when you can describe how access decisions are made instead of relying on vague statements like only authorized users can access it. Access control models are the mental frameworks that define who is allowed to do what, based on what rules, and enforced at what point in the system. Beginners often learn about permissions as if they are just a list of checkboxes, but those checkboxes are the surface layer of a deeper design choice. What logic determines access and what assumptions are built into that logic? The models we're covering: role-based access control, RBAC, attribute-based access control, ABAC, mandatory access control, MAC, and discretionary access control, DAC. Each represent a different way to express and enforce trust. They are not interchangeable vocabulary words, and using them precisely matters because different systems and risks require different models. We also need to connect these models to enforcement points, because a model that exists only in policy is useless unless the system has a place where it can actually enforce the decision. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Before we dive into the individual models, it helps to separate identity, permissions, and enforcement in your mind, because beginners often blend them together. Identity is who or what is requesting access, such as a user account or a service identity. Permissions are what actions are allowed, such as read, write, delete, approve, or administer. Enforcement is where the system checks whether the request should be allowed and then permits or denies it. The access control model describes the logic that maps identity and context to allowed actions, and it determines how permissions are organized and applied. When people say access control failed, the failure might be in any of these layers, such as a weak identity check, a poorly designed permission set, or an enforcement point that can be bypassed. Precision means you can explain which model you are using, what the rules are, and where they are enforced. In cloud security, this precision is critical because access is often distributed across many services, and inconsistent models create gaps where one system trusts what another system never intended. Role-based access control, RBAC, is one of the most common models because it fits how organizations naturally think about work. In RBAC, permissions are assigned to roles, and users are assigned to roles, which means access decisions are based largely on what role a user has. A role is meant to represent a job function or responsibility, such as help desk technician, billing specialist, or system administrator. The strength of RBAC is that it simplifies management, because you can grant or remove access by changing role membership instead of editing dozens of individual permissions. It also supports consistency, because everyone in the same role receives the same baseline permissions. Beginners sometimes misunderstand RBAC and think it means everyone gets one role, and that role never changes. But real environments often use multiple roles per user and allow role membership to change as responsibilities change. The design challenge is to keep roles meaningful and not let them become overly broad buckets that grant far more than needed. When RBAC is designed well, it supports least privilege by making roles narrowly aligned to real duties and by separating sensitive administrative roles from general user roles. RBAC has a common failure mode that beginners should recognize, which is role explosion and role creep. Role explosion happens when you create too many roles to account for every edge case, making the model hard to manage and understand. Role creep happens when roles become more powerful over time because teams keep adding permissions to avoid access requests, turning roles into convenience bundles rather than least privilege designs. Both problems reduce security because they make it unclear what access is justified, and they increase the blast radius of compromise. The best way to keep RBAC healthy is to design roles around stable job functions, keep privileged roles separate, and use temporary elevation for exceptional tasks rather than permanently expanding roles. This is where review processes matter, because roles should be audited and refined based on real usage and risk, not based on the loudest complaint. RBAC is powerful because it maps to organizational structure, but it requires discipline to keep it aligned with real responsibilities. When you use RBAC precisely, you can explain which roles exist, why they exist, and what permissions they grant, which is far more defensible than a messy collection of individual grants. Attribute-based access control, ABAC, takes a different approach by making access decisions based on attributes rather than fixed roles. Attributes can describe the user, such as department, clearance level, or device posture, and they can describe the resource, such as sensitivity level, owner, or location, and they can describe the environment, such as time of day or network context. In ABAC, policies evaluate these attributes to decide whether access is allowed, which makes the model more flexible than RBAC. This flexibility is valuable in cloud environments where context changes frequently and where you may need to enforce conditions like only allow access to sensitive data from managed devices or only allow administrative actions from a trusted network segment. Beginners sometimes think ABAC is just a fancier version of RBAC, but it is a different way of expressing policy because it emphasizes rules that adapt to context. The trade-off is complexity because you must manage attributes reliably and ensure policies are tested and understandable. If attributes are wrong or missing, decisions can become incorrect, either denying legitimate access or granting unauthorized access. ABAC can solve problems that RBAC struggles with, especially when access depends on context rather than just job function. For example, a user might normally be allowed to read certain data, but only when their device meets security requirements, or only during business hours, or only when they are physically in a certain region. These conditions can be difficult to represent cleanly with roles, because you would need many roles to cover every combination. ABAC expresses these policies more naturally, but it requires careful design so policies remain predictable. A common beginner misunderstanding is to assume that more conditions automatically means more security, but overly complex policies can create blind spots and operational mistakes. The best ABAC policies focus on a few high-value attributes that are reliably measured and clearly connected to risk. They also require good logging, because when access is denied or granted based on attributes, you need evidence of which attributes were evaluated and how the decision was made. That transparency is part of precision, because a model that cannot explain its decisions becomes hard to trust and hard to audit. Discretionary access control, DAC, is a model where the owner of a resource can decide who else gets access to it. In DAC, access control is discretionary because it is at the discretion of the resource owner, such as a file owner granting read access to a colleague. This model is common in file systems and collaboration platforms because it supports flexible sharing and productivity. The security benefit of DAC is that it allows decentralization, which can reduce bottlenecks, but the security risk is that it can lead to inconsistent protection and accidental oversharing. Beginners often assume that if someone has access, it must have been approved by a central authority, but in a DAC environment, access may have been granted informally by an owner with limited security understanding. DAC can also create complex access graphs where many people gain access through a chain of sharing. This is why DAC is often paired with broader governance controls, such as classification labels that restrict external sharing or auditing that flags unusual sharing patterns. When you apply DAC precisely, you recognize that it is not inherently bad, but it requires guardrails because it empowers users to make access decisions that can have large consequences. Mandatory access control, MAC, is a model where access decisions are enforced by a central authority and users cannot override them. In MAC, resources and users are assigned security labels, and the system enforces rules based on those labels, such as preventing a user without sufficient clearance from accessing high-sensitivity data. The key idea is that access is mandatory because it is dictated by policy and cannot be changed by the data owner or the user. MAC is often associated with high-security environments where strict information flow control is required, and it emphasizes confidentiality and controlled dissemination. Beginners sometimes confuse MAC with simply having strict permissions, but the defining feature is the inability of individual users to change the access rules for their own convenience. This can reduce the risk of accidental leakage because even well-intentioned users cannot share restricted data outside of policy. The trade-off is reduced flexibility, because strict rules can slow collaboration and require formal processes for access changes. Precision here means understanding that MAC is about centrally enforced labels and rules that users cannot bypass through discretionary sharing. These models can be used alone or combined, and beginners should be careful not to assume that combining models always improves security. A combination can be powerful when the models address different needs, such as using RBAC to manage baseline job access, ABAC to add contextual conditions for sensitive actions, and DAC for flexible sharing within boundaries. However, combining models can also create confusion if it is not clear which model has precedence or how conflicts are resolved. For example, if a file is shared through DAC but labeled as high sensitivity under ABAC-like policy, the system must clearly enforce which rule wins. Otherwise, you get inconsistent behavior and unpredictable protection. A precise design defines conflict resolution rules, such as always enforcing the most restrictive applicable policy, and it ensures those rules are implemented consistently across systems. In cloud environments, where services might implement different default models, precision becomes even more important because inconsistency becomes an attack surface. Attackers look for the weaker enforcement path. An inconsistent model application often creates that weaker path. Enforcement points are where access control becomes real, and they are often overlooked because people focus on models and forget where decisions happen. An enforcement point is the place in the system where an access request is evaluated and allowed or denied, such as an application gateway, an API endpoint, a database permission check, or a file access control check. If enforcement points are incomplete, attackers can bypass them by reaching a backend directly or by exploiting a path that was not protected. This is why architecture matters so much. You want to route access through controlled choke points where policies can be enforced and logged. For example, if an application checks permissions in its user interface, but the underlying API does not enforce the same checks, an attacker can call the API directly and bypass the intended restrictions. Beginners should learn that access control must be enforced at the point of action, not just at the point of display. Enforcement points should also generate logs that record decisions, because without logs you cannot audit access and you cannot detect abuse. A model without enforcement is theory, and enforcement without logging is a blindfold. A subtle but important aspect of enforcement points is that they must be consistent across the system and aligned with how systems are actually used. If users access data through multiple interfaces, each interface must enforce the same policy, or you will create an accidental bypass. If a service is accessed by both humans and automation, the enforcement must handle both identity types and apply the same underlying rules. In cloud environments, enforcement points may exist in multiple layers, such as a platform access policy and an application-specific policy, and you need to understand how those layers interact. If the platform grants access broadly but the application tries to restrict it, you may still expose data through alternative access methods. Conversely, if the platform restricts access but the application assumes broad access, you might cause operational failures that lead to unsafe workarounds. Precision means you map policies to enforcement points explicitly, and you test that the enforcement holds under normal use and under abuse attempts. When enforcement is clear and consistent, the model becomes dependable and easier to reason about. As we wrap up, applying access control models precisely means understanding that RBAC, ABAC, DAC, and MAC are different approaches to organizing and enforcing trust, and choosing the right approach depends on the environment and the risk. RBAC provides manageable role-based structure but requires discipline to prevent role creep. ABAC provides flexible context-aware policy but requires reliable attributes and careful testing to avoid complexity becoming a vulnerability. DAC supports flexible sharing but needs guardrails and monitoring to prevent accidental oversharing and inconsistent protection. MAC enforces centrally controlled information flow and can reduce leakage risk, but it trades flexibility for strictness and requires clear labeling and rule enforcement. Enforcement points turn these models into real protection by ensuring access decisions are made at the moment of action and cannot be bypassed through alternate paths. When you can describe which model is in use, what the rules are, and where they are enforced, you are no longer guessing about access control. You are engineering it, and that precision is exactly what SecurityX expects you to demonstrate when analyzing modern systems.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.